Yes, hello guys. My name is Benedict Kimutuo, and I am presenting to you a presentation about mutually agreed norms for routing security (MANRS) as part of my initiative for the cause that was offered by Internet Society. The name of the course is called Securing Global Routing. So, what is MANRS? Mutually agreed norms for routing security. It is a global community that is made up of security-minded network operators who share a number of important beliefs. Those beliefs are they care about routing security, they are prepared to spend resources on routing security, they're also prepared to be held accountable by the community. So this mutually agreed norms for routing security, it is an initiative that is supported by the Internet Society to provide crucial fixes to reduce the most common routing incidents. Internet Society recommends that different ISPs, content delivery networks, enterprises to join MANRS community in order to improve your security posture and reduce both the number and impact of routing incidents on a global scale. So, what are the routing system security threats? There are three common routing threats, which are prefix hijacking, also known as BGP hijacking or route hijacking. Another one is route leaks, and the last one is IP spoofing. I'll be explaining each one of them in details. You should take note of this diagram. I'll get back to it. I'll also be explaining each of the routing incidents. Now, BGP hijacking. It is when an attacker disguises himself as another network provider by announcing the prefixes that are belonging to another autonomous system, as if those prefixes were belonging to that particular attacker. Now, if this information is propagated into the global internet, it will distort the roadmap of the internet, thereby hijacking the proper prefixes that belong to another autonomous system. Now, the repercussions of such incident is that it can cause denial of service attacks or traffic interception. Now, the solution to such an attack is by implementing strong filtering policies. Now, another routing incident is I'll give you an example of prefix hijacking. There's this incident that occurred in 2008 whereby this internet service provider in Pakistan known as Pakistan Telecom with autonomous system number is 17557, they had an intent of blocking YouTube in their country, Pakistan. Therefore, they were announcing prefixes that were belonging to YouTube to the whole of the country, actually to their customers, so that their customers may not be able to access YouTube content. Now, one of the this ISP's upstream provider, that was Pakistan Telecom with autonomous number AS3491, ended up forwarding this announcement to the rest of the internet, which thereby resulted in downtime of YouTube, hijacking YouTube traffic on a global scale. Now, you can get more information about this incident by visiting this link. You can see it over here. You can visit this link, which is hosted by the RIPE NCC website. This is a regional internet registry for Europe. You can get more details about the timeline, how it happened, how YouTube mitigated this event. You can also see the BG Play snapshots. BG Play is a system that shows real-time events of a particular routing incident. And as you can see from this diagram, this box with the red color, this is YouTube autonomous system number, and this one is Pakistan. This is Pakistan Telecom autonomous system number. Let me check that. Yes, that is Pakistan Telecom Autonomous System number. So initially, when Pakistan Telecom unauthorized announcing prefixes belonging to YouTube, all YouTube traffic in the internet were directed to Pakistan Telecom. But eventually, YouTube mitigated this traffic by announcing a prefix with a more specific prefix length, thereby which is more preferred by the eBGP sessions. Yeah, so that's how YouTube, in a nutshell, that's how YouTube mitigated this attack. You will get more information for this attack in this link. You can just go and visit this link. Okay. Now another attack is known as route leak. Route leak, it is the propagation of routing announcements beyond the intended scope. This is mainly caused when a particular network operator is having more than one upstream provider, thereby announcing to one upstream provider that it has a path to a destination that is found in another upstream provider. You see here, a network operator with multiple upstream provider announces to one upstream provider that it has a route to a destination through the other upstream provider, and this is often caused by misconfiguration, accidental misconfigurations. Now, the replications of such a routing incident is that it can be used for traffic inspection. This is, of course, if the attack was done purposely. The solution for such an attack is by implementing strong filtering policies. Now, another attack is known as IP spoofing, whereby IP spoofing, it is the forging of the source IP address field that is found in the IP header of a normal IPv4 packet or IPv6 packet, with the purpose of concealing the identity of the sender or impersonating another computing system. Now, the replication of such an attack, it can be used in reflection amplification denial of service attack. We'll see this in the upcoming slides. So, solution for such an attack is by implementing source address validation. Now, let's get back to our previous diagram. Now, consider this autonomous system which has two customers. It is pairing with this autonomous system. Now, this is the transit provider. Now, for the case of prefix hijacking, if there was another autonomous system number that could be announcing the prefixes that belong to this autonomous system number, then that could lead to traffic that is destined to come here to go to another autonomous system number that is, run by an attacker. So you'll be seeing a lot of this diagram. It will be used in explaining these various routing incidents. Now let's get to the MANRS core principles. There are 4 core principles that are implemented by mutual agreed norms for routing security. They say that they recognize the interdependent nature of the global routing system, and they also recognize their role in contributing to secure and resilient internet. They will also integrate best current operational practices related to routing security and resilience in our network management processes in line with the actions. You will see these actions in the upcoming slides. There are 4 concrete actions that are to be implemented by the participants of the MANRS community. Now, the third principle is they are committed to preventing, detecting, and mitigating routing incidents through collaboration and coordination with peers and other ISPs in the line of actions. Now, in line of action, there's one action of MANRS which states coordination. Coordination is one of the actions that is implemented by the MANRS community, and it is also used in the MANRS core principles. They also encourage their customers and peers to adopt these principles and actions. Now, these are the MANRS concrete actions or pillars: global validation, filtering, anti-spoofing, and coordination. Now these actions, they are, as it is stated here, they are technologically neutral, so they can be implemented globally, regardless of the vendor of the equipment that you're using. Let's start with global validation. Now, in order to facilitate the validation of routing information on a global scale, network operators must publish their routing information so that other parties can validate it. Now, there are various databases and repositories that are used by network operators to publish their routing information. We will get to that in the upcoming slides. For now, you should know that global validation is a very important action of MANRS community that is used to help other network operators to validate routing information of other network operators. Filtering. Now, in order to prevent propagation of incorrect routing information, network operators must ensure correctness of their own announcements and announcements from their customers to adjacent networks with prefix and AS path, autonomous system path granularity. That means that the prefixes and the autonomous system path should match in a more efficient manner in order to prevent propagation of incorrect routing information. Now we'll get to that in the upcoming slides. You'll understand it more. Anti-spoofing. Now, in order to prevent traffic with spoofed source IP address and the IP packet of the IP header of the IP packet, network operators must enable source address validation for at least single-homed customer networks, their own end users and infrastructures. Now, what are single-homed stub customer networks? Single-homed stub customer networks are networks or internet service providers that have only one upstream provider. They do not have multiple upstream provider. Now, if you are an ISP and you have multiple customers, and those customers only rely on your network, they do not have any other transit provider. Now, you should implement source address validation for such customers, together with their own end users and infrastructures, in order to prevent these routing incidents, such as IP address spoofing. Coordination. As I said before, coordination, it is another important action of MANRS community. In order to facilitate global operational communication and coordination between network operators, they must maintain a globally accessible and up-to-date contact information. Now, this contact information can be registered in various databases such as Internet Routing Registries, Resource Public Infrastructure, and Peering DB, which we will look into in the upcoming slides. Yes, now these are the databases and repositories that network operators must use to document their routing information. IRR, which stands for Internet Routing Registry, Resource Public Infrastructure, and Peering DB. Let's start with Internet Routing Registry. IRR, it is a public database of internet route objects. It is used for determining and sharing routes and other related information with other network operators, mainly for the purpose of configuring routers. Now, every regional internet registry operates its own in-house IRR database, with an exception of LACNIC, Latin American and Caribbean's Network Information Center. Now, visiting this link, you will see the list of routing registries. You can see it over here. Now you can see AFRINIC, AFRINIC for Africa, APNIC for Asian Pacific. You can see ARIN for American Registry for Internet Numbers. You can also see RIPE NCC, RIPE, here it is for the European region, but you don't see LACNIC. LACNIC does not operate its own in-house Internet Routing Registry. Instead, it depends on RIDB, You'll see in the upcoming slides, RADB, it stands for Routing Assets Database. This is it is a company that is mainly concerned with implementing routing registries. It is an aggregator. It receives different route objects from different that are implemented in different routing registries, deployed in different regional internet registries. So LACNIC depends on RADB or NTT-COM. These two guys are aggregators. They aggregate information from different IRR databases. Okay, as you can see here, Routing Assets Database, also expanded as Routing Arbiter Database. It is a lookup database that is run by this company known as Merit Network, designed to make fundamental information about networks available. Now, what are the fundamental information about network? Routing information. It consists of different objects such as outnum object, AS set object for the customer con, route and route 6 for the prefixes. Various objects are found in routing registry. We also have NTT-COM. You can also visit their websites. Now this is RADB, which is run by Merit. They also have their own browser integrated method of querying such routing information. We'll get to it in a moment. They also have their query help. I will show you. We also have NTT-COM. You can go ahead and Google it. As you can see from this diagram, aggregators are RADB. This is a Routing Asset Database, and NTT-COM. These are two aggregators that they aggregate routing information from different routing registries, including the ones that are run by regional internet registries and the ones that are also run by themselves, RADB and NTT-COM. You can see here. Now this BGPQ3, this is a tool that is used to request information from different routing registries. We'll see that in upcoming slides. Let's do this demo and see how you can now different regional internet registry run their own in-house WHOIS server, which at the same time runs its own routing registry. That's why you can see we're using the WHOIS client to poll for information about routing registry. Now with this command, we are polling information about, we're querying the routing registry server deployed by NTT-COM for information about this. This is known as an AS set, autonomous system. It is a set of autonomous system numbers or another set of AS set. You can see here from the output of this command. You see, it returned an AS set object. If you see in the description, you see it belongs to the entity Global IP Network Transit version 4 customers. Now the members of this AS set itself, the NTT-COM company itself, it's one of the members of this AS set object, but it also consists of other autonomous system numbers, as you can see this one. But you can see here we have another AS set. The syntax of AS set, it consists of autonomous system number, colon, and then the name of the AS set. the format of writing this is defined by RPSL, routing policy specification language, which we'll look in a moment. You can see the admin contact, technical contact, remarks, and all that. Source entity.com, because we requested this information from their own routing registry servers. Now this second command, we are querying the routing registry servers deployed by entity.com for information about IPv6 prefix. It will return a Route 6 object, as you can see here. Now, as I told you before, that entity.com, it is an aggregator. It aggregates information from various routing registry. That's why I have multiple Route 6 objects. This one comes from ARIN. The first Route 6 object, it comes from ARIN. The second one, it comes from, now this is a route object that was converted from an RPKI object, RPKI raw object, route origin authorization. We'll look into that in a moment. You'll understand that. As you can see here in the remarks, this route object is the result of an automated RPKI to IRR conversion process. Now they are converting RPKI raws to IRR in order to get various objects that are to be implemented in IRR servers. The third Route 6 object comes from RIPE. So you can see two Route 6 objects coming from two different regional internet registries, and one that is a result of an RPK to IRR conversion process. Now let's talk about RPKI, Resource Public Key Infrastructure. Now RPKI, it is a public key infrastructure based service that allows users to certify the internet number resources in order to help others secure internet routing. Now, what are the internet number resources? The internet number resources that I'm talking about here are ASNs, autonomous system number, and the prefixes, be it IPv4 or IPv6. Now, it is used to let a legitimate holder of a block of IP addresses to make an authoritative statement, which is known as ROA, route origin authorization, about which autonomous system number, which autonomous system is authorized to originate their prefixes in the BGP, in the global routing table. Now, in turn, other network operators can download and validate these statements and make routing decisions based on them. Now, in order for network operators to download these statements, they have to install something called RPKI validators, and they have to configure their global BGP routers to communicate with their in-house RPKI validators, which hold a local cache of their RPKI repository in order to make routing decisions. Now, this process is referred to as route origin validation. This provides a stepping stone to provide path validation in the future. So currently, we're only able to provide origin validation, route origin validation, but we are intending to be able to provide path validation, which is still in progress. People are still working on it. Now, in addition to providing information to internet routing registries, it is recommended to register the routes you originate, and encourage also your customers to register their routes they originate within an RPK repositories by creating ROA, route origin authorization objects. Now, what is a ROA? A route origin authorization object, they are cryptographically signed objects which state which prefixes an autonomous system is authorized to originate. Now, this is an example of a ROA. As you can see, it states the autonomous system number, it states the prefixes, it also states the maximum prefix length, that this autonomous system number is authorized to announce or to advertise in the global routing table. it also consists of the validity period. Now, internet number resource holders, I mean whether it is a national internet registry or whether it is a local internet registry, which can be an ISP, a CBN, an enterprise, they have to obtain a resource certificate ensuring that a set of IP addresses prefixes has been assigned or allocated to them. Now, this resource certificate is obtained from the regional internet registry where you are currently residing in. If you are an ISP or an enterprise in Africa, you have to obtain a resource certificate to your regional internet registry, which is AFRINIC. Now, you also have to create route origin authorizations that specify an IP address prefix length, and an originating ASN. Now, these ROAs are created by network operators and used by other network operators to make routing decisions. As I said earlier, the ROAs provide verification that the routes being advertised are correct and can be used safely in routing tables. Now, network operators need to obtain an RPK validator and install it. Now, this is what I was talking about earlier, that they have to install an RPKI validator. There are plenty of them. After installing them, they have to download a local cache of the RPKI repository. That means it will consist of all the ROAs that are installed on all RPKI repositories run by different regional internet registries. Now, you should configure your routers participating in eBGP sessions to contact this RPK validator in order to compare the announcement that the router it has received from the global routing table with the actual ROA found in the local cache in the RPK validator. Now, RPK chain of trust. As you can see, each regional internet registry is running its own root certificate authority. It also issues a trust anchor that is used by the local internet registry, which can be an ISP or an enterprise, to cryptographically sign their resource certificate, which eventually signs their own ROAs that they create using their member portal in their specific RIR website. Now, LACNIC and APNIC, these are the two RIR that have that they consist of also national internet registries, as you can see here. Now, national internet registries also act as child certificate authorities to the root certificate authorities of regional internet registries. As you can see, this hierarchy is similar to the normal public infrastructure. Now, the 5 RIR each run a root certificate authority with a trust anchor from which a chain of trust for the resources they each manage is derived. Now, resource certificate. Now, the digital certificates used in RPKI are based on the legacy X.509 along with the extensions for the IP addresses and the AS identifiers. You can read this RFC for more details. Now, these certificates are called resource certificates, RC. They differ from the commonly known X.509 public infrastructures, such as those that are used in SSL, since they do not include identity information, as their only purpose is to transfer right to use internet number resources only. So they just show that this particular regional internet registry is giving this particular ISP the right to use this block of IPv4 or IPv6 address and using this autonomous system number, be it 16-bit or 32-bit autonomous system number. I mean 32-bit or 64-bit ASN. They also do not rely on a vast number of root certificate authority, which come pre-installed in a browser or an operating system. RPKI relies on just the 5 trust anchors that are run by the 5 RIRs. Now the creation of ROA is solely tied on the IP address space that is listed in the certificate and not the AS number. This means that the holder of that particular certificate can authorize any autonomous system number to originate their prefix, and it's not a must for only the autonomous system number to originate their prefix. Now, validating routes. Now, once ROA is validated, now the resulting object is called validated ROA payload, VRP, which consists of the IP prefix, the maximum length, and the origin autonomous system number. Now, any operator is free to get a list of ROAs from RIRs and use it to tell their routers to take action based on the ROA. When comparing VRPs to the announcement that are received from ABGP sessions, the following statuses are possible. Valid. This means that the route announcement as seen from the global routing table is covered by at least one VRP. The term covered means that now the prefix in the route announcement received by a specific BGP router is equal or more specific than the prefix in the matching VRP. Now we'll come to talk about this part more specific. Now an attacker can announce a more specific prefix length that you have registered in a ROA, and he can append the appropriate ASN, and he will be able to announce your prefixes. I mean, other routers implementing RPK won't be able to invalidate such an announcement. So this means that all the prefixes you should announce all the prefixes you have created in a ROA up to the most specific prefix, because it can be manipulated or used by an attacker to create such an attack. Now, invalid. This means that the prefix is announced from an unauthorized autonomous system. The announcement is more specific than that is allowed in the maximum length of the set in that particular VRP. Now, if an operator is using RPKI in a strict version, odds are good that this announcement will not be installed into their routers. Now, the third status is not found. This means that the announcement received in the global routing table is not covered, or it is partially covered by VRP entry in the local cache of the RPK repository. Now, this is the default state if no ROA has been made for the announcement. It is expected that all operators will allow these routes to be installed in their routers. Now let's do this demo. Oops, sorry. Now, BGP Mon, it is a monitoring system that implements RPKI system. So we are actually sending a request to the RPKI database that is deployed by BGP Mon, to request a ROA for this particular autonomous system number, and this IPv6 prefix combination. Okay, something is wrong in my syntax. Let me correct that. I can see it. Yes. So the answer here is valid. It means that there is a particular validated ROA payload that is found in the BGP MON RPK database. As you can see here, this autonomous system number is authorized to announce this IPv6 prefix with this maximum length set, and it is valid from this date to this date. It also tells you when it is expiring, 58 days, 6 hours and all that. Let's do this another example for IPv4 prefix. You see, now this means that there is no ROA that matches this combination of ASN and IPv4 prefix. Now, which gets us to this another important platform that network operators use. It's called IRR Explorer. You can use this to compare the prefixes that you have registered in a particular internet routing registry, be it an in-house hosted IRR in a particular regional internet registry, or the ones that are found in these aggregators such as EntityCom and RIDB, all the objects that you have registered, the raw objects that you have registered in a particular RPK repositories. It is comparing these objects with the actual announcements that are seen from the global routing table. Now let's try these examples. I already have this website loaded. Let's wait for it. Yes. Now you can see from the global routing table, we can see this prefix is announced by this autonomous system number, but at the same time it is announced as it is seen from the RPK repository. The same ASN announces this IPv4 prefix as it is seen from this EntityCom internet routing registry, the same ASN. Now this platform, it gives you different colors that shows the different severity of different scenarios. As you can see here, advice, it looks good. BGP origin consistent with ASN and route objects. With AS, by route objects they mean the route objects that are installed in internet routing registries, such as, for this case, it is EntityCom, not RIDB. It seems this ISP has created, it has documented its network routing policy in EntityCom routing registry. Now you can see, you can go through these lists and you can see multiple scenarios. like you can see this case, multiple route objects exist with different origins. This means that this IPv6 IPv4 prefix is announced by different it is announced by different autonomous system number as seen from different places. As it is seen from BGP, this autonomous system number is announcing this prefix. From RIDB, this one, and from what is this, RIPKI, this one. From NTTCom, so RIPKI and NTTCom, they analogous, they show the same autonomous system number, and the BGP. The only difference comes here from RIDB. Yes, RIDB shows a different autonomous system number originating this IPv4 prefix. Let me see my internet service provider, Habari node, by including its autonomous system number 609. So this shows that this ISP there it is. Okay. It shows all the prefixes that are announced by this autonomous system number, Habari node. It has its entries in RIDB. It has documented its network routing policy in RIDB. Now the autonomous system number seen in this RIDB IRR is consistent with the one that is seen from the global routing table. So you can go through this and learn what's actually going on here. You can see these other IPv4 prefixes. They're not seen in BGP, but they are seen in the RIDB. In what is it? They can be seen in Afrinic, WHOIS database. That means this ISP is not including this this block of IPv4 addresses in its eBGP sessions. It's not announcing these IPv4 addresses. Yeah, you can continue testing these other two ASNs. Now, this takes us to another platform that is used for documenting your routing information. It's called the PeeringDB. Now, the PeeringDB, it is an open resource for networks to share their peering information with other networks amongst each other. Each network is responsible for maintaining its own records. Now, a PeeringDB record allows you to consolidate your network information in a single location, and also helps you to look up information about other network information. That means if you want to do peering with another ISP, you have to, the first place to look for their network information, you go to the PeeringDB, you see the information, including contact information. Now, PeeringDB records are used to supplement routing information stored in these other repositories, be it IRR or RPKI repository. Now, it lets you publish routing information to let other networks know about your networks and how to contact you. It is the first stop when deciding where and whom to peer with. Now, in order to use the PeeringDB, you must register an account. After registering an account, you should request affiliation to your organization or your autonomous system number to unlock full access to data, for example, non-public network contact information. Now, this non-public network contact information means that anyone cannot be able to fetch network contact information for a particular ISP if you do not have an account in PeeringDB. You can get other information, but those important information, you can get them unless you have logged in with your account and then search that particular ISP. You will get the network contact information. Now, I have this site already loaded. Here it is. We can look information about my ISP Habari node. Let me search by using autonomous system number 36909. There it is. Now you can see information like company website, ASN, route set or AS set as seen in IRR, IPv4 prefixes. There are 50 IPv4 prefixes and 1 IPv6 prefixes. You can see information about their public peering exchange points. You can see information also about their private peering facilities. As I told you earlier, you can't see contact information. You see some of these network contacts are hidden because they're only visible to authenticated users, and you are currently not logged in. I don't have an account in PeeringDB, so I cannot be able to find network contact information. But this is one of the databases that network operators use to document the information so that other people can look up the information and contact them in case they want to peer with them or anything. Now let's start with the first MANRS action, which is global validation. Now MANRS participants should perform the following actions in order to facilitate routing information, validation of routing information in a global scale. First, they have to communicate their correct announcements with other networks that are adjacent to them. They also have to publicly document their network routing policies, autonomous system numbers, and prefixes that they intend to be advertised to external parties. Now, the MANRS action for global validation requires network operators to ensure that their network routing information is publicly available. Now, this includes the announcements that network originates, as well as the routing policy describing how reachability information exchanged with other networks is handled. Now, that specifically covers routes that are announced to other networks, the eBGP routes. Now, this is an example of prefix hijacking. Consider this autonomous system number, which is a transit provider. In the upcoming slides, you'll see how an attacker can advertise a prefix belonging to another autonomous system number, thereby hijacking traffic for that particular victim. Now, an attacker with this particular autonomous system number, ASX, is announcing prefix. This prefix belongs to this customer with autonomous system number 64502. Now, this attacker is announcing prefix that it doesn't belong, that it doesn't have access to its transit provider. Now, if its transit provider is not implementing any of this MANRS action, it doesn't use IRR or doesn't use RPKI to validate its inbound announcements, it will end up propagating this traffic to the rest of the internet, which eventually reaches this autonomous system number A. Now, the customers of this autonomous system number, if they want to access traffic, to access content that is maybe hosted by autonomous system number this 6502, this traffic will be hijacked. Instead of going to the appropriate ASN, this traffic will go to this attacker autonomous system number, which you can do multiple stuff such as traffic inspection and all that. Now, if this autonomous system number had published its own network routing policy, then it will be able to mitigate the threat of prefix hijacking. Therefore, this autonomous system number, which is the transit provider for this attacker, will be able to query the IRR database to see if this autonomous system number is authorized to announce this prefix. Now, if it does that, now traffic will be directed to the proper authorities, to the proper autonomous system number. Sorry, I was referring to this autonomous system number 64501. Now, in order to facilitate origin validation, MANRS participant must meet certain requirements, which are they have to register their network routing policy by taking advantage of the outnum object in the IRR repository. They also have to register the expected announcements by taking advantage of the route object or route 6 object for the IPv6 case. They also have to document their customer con by creating an AS-set object, which consists of the autonomous system numbers of all of its customers. They also have to ensure that their customers also register the expected announcements by using route or route 6 objects, which we will cover in the upcoming slides. They also have to register their expected announcements to an RPKI repository and ensure that their customers do the same. Now, as I said before, that all regional internet registry host their own internet routing registry, with an exception of LATNIC, Latin America and the Caribbean, whereby for ISPs or autonomous systems operating in this region, they have to either choose RIDB maintained by Merit Company or EntityCom. Now, you should register your expected announcements within a route or 6 object and document your customer con within an AS-set object, as I said earlier. Both of these objects will be used when documenting your network routing policy, which is eventually stored in an outnum object. Now, you should create a route 6 or route objects to document which address prefixes an autonomous system number is allowed to announce. As you can see here, this autonomous system number is allowed to announce this IPv6 prefix. Therefore, the administrative network operator of this ASN has to create route 6 object in a particular IRR. Route or route 6 object indicates the prefix that the particular ASN is allowed to announce. Now, the origin just specifies that particular autonomous system that is allowed to announce that prefix. Now, for a network to document its customer con, network operator should create an AS-set object that consists of all of its customers, including itself as its members, as you can see from this members attribute of this AS-set object. Members attribute, it contains a list of direct members of that particular set, which can either be a list of other AS-set names or autonomous system numbers. Now, the TEC, short for technical contact, it references the details of technical contact, which can be a single person or a role within an organization that more than one person takes on. Now, admin contact, it also references the on-site administrative contact, which can be a single person or a role within an organization that more than one person takes on. Maintained by attribute specifies the maintainer of your organization to protect the route. You'll see in the upcoming slides that this attribute, it references the maintainer object, which is used to protect the objects of a particular IRR registry. Now, the outnum object. Now, a network routing policy of an organization is documented within this particular object, which is eventually stored within an IRR. Now, taking an example at this diagram, and this outnum object over here. Now, the outnum attribute has a value of the autonomous system number of that particular autonomous system. Description describes. Now, network administrators or network operators use the remarks attribute for describing further information. Now, it's stating its customers. So you can see this autonomous system number has two customers, 501 and 502. Therefore, from 501, using this attribute import, from this customer I want to accept only traffic originating from its autonomous system number, but to it I want to announce any. From this other customer I want to accept traffic originating from this autonomous system number, but to it I want to announce any. Now for peers, from my peer 511 64 511, I want to accept this traffic with this autonomous system set. This is an AS set, but to it I want to announce my AS set. As you can see, this is the AS set of